Picture this. It's 1969 at Harvard's Aiken Computation Lab. A computer scientist named W.A. Woods publishes a paper that's about to change everything we thought we knew about machines and language. You see, this was the moment a computer learned to do more than just scan words. It learned how to understand the deep, hidden structure of a sentence. But to really get why this was such a huge deal, we first need to look at the massive brick wall computer science had just run into.
So, to see why this was such a monumental leap, let's start with a challenge. And forget about a machine for a second. Can you easily understand this next sentence?
Go ahead, take a second. It's a perfectly grammatical English sentence, but yeah, it's a nightmare to untangle, right? This kind of nested or center-embedded structure is precisely where the computers of the 1960s just completely fell apart.
So why was this so hard? I mean, what was the big deal? The problem wasn't the computer's speed or power. Nope, it was the entire model they were using to think about language itself.
Back then, the main tool for the job was something called a finite state machine. The best way to think about it is like a train on a single, one-way track. It can only move forward one station or one word at a time. It knows where it is right now, but it has absolutely zero memory of the stations it visited before. As Woods himself put it in his paper, this model was just grossly inadequate for language.
And that's the absolute heart of the problem. Human language isn't a flat train track. It's this complex, tangled web of ideas tucked inside other ideas. To understand that the cat sat on the mat, you have to hit pause, dive into a little side story about the dog that chased it, and then hit pause again to figure out the man who owned the dog. A finite state machine just can't do that. It doesn't have a pause button. It gets completely lost.
And this is where W.A. Woods' breakthrough really begins. He realized that for a machine to understand us, its grammar needed a way to pause, go figure out a subproblem, and then jump right back to where it left off. In other words, grammar needed a memory.
His first big step was the Recursive Transition Network, or RTN, and it introduced a really powerful idea. What if grammar isn't one giant sprawling map, but a collection of smaller, specialized maps? So when the main network runs into something complicated, like a noun phrase, it doesn't try to solve it right there. Instead, it's like it makes a phone call to a specialist, a dedicated noun phrase map.
So how does it remember to come back? It uses something called a push-down store, which is really just a fancy term for a memory stack. When the main network calls up that noun phrase specialist, it pushes its current location onto the stack, like leaving a bookmark. The specialist does its job, and when it's done, it pops that bookmark off the stack, and boom, the main network can pick up right where it was. This simple push and pop is the secret to handling all that nested language.
But here is where we get to the real genius. Okay, so recursion was a huge step, but it only let a machine give a thumbs up or a thumbs down. Yes, this is a valid sentence, or no, it isn't. It couldn't tell you what the sentence actually meant. Woods' true innovation was to augment the network, to give it the power not just to recognize language, but to actually understand it.
And this is the key difference between what's called a recognizer and a transducer. An RTN is just a recognizer, but the Augmented Transition Network, the ATN, is a transducer. It doesn't just validate the sentence, it's actively building a blueprint, a structural description of what the sentence means as it goes along. He did this by adding two powerful new tools to every single path in the network. First, a condition. Think of it like a bouncer at a club. It's a test that has to be true before you can go down that path. Like, hey, does the noun here agree with the verb? If the answer is no, you're not getting in. And second, an action. If the condition is met, the network actually does something, like taking the noun it just found and storing it in a little memory box labeled subject.
And this is what led to this brilliant insight. The ATN isn't just a static map of grammar rules anymore. With these conditions and actions, it becomes a living, breathing program, something that can test ideas on the fly and actively build meaning piece by piece.
All right, enough theory. Let's actually see this program in action. We're going to trace the ATN as it parses a simple question from Woods' paper, Does John like Mary?
Okay, the parser starts up. It sees the first word, does, and immediately recognizes it's probably the start of a question. So it follows a path that has a couple of actions attached. First, it fills a register called type with Q for question. Then it puts the word does into the AUX register. Easy enough. Next up is John. The network expects a subject here, which is usually a noun phrase. So, what does it do? It makes that recursive call.
It pushes to the noun phrase subnetwork. That little specialist network quickly identifies John, packages it up, and pops back. The main network then takes that result and, as its action, drops it right into the subject register.
Now it sees the word like. It figures out this is the main verb. The action here is super simple. It just sets the V register to like and moves on. Finally, it gets to Mary. The network knows that a verb like needs an object, so it pushes to the NP network one more time, which returns the result for Mary. And now, this next action shows you the real power. It doesn't just store Mary. It takes the verb from the V register, combines it with the noun phrase it just found, and builds a whole new component, a complete verb phrase, and places that entire thing into the VP register.
So at the very end of the sentence, this is what we're left with. It's not just a yes. It's a full, structured analysis. It tells us this is a sentence that's a question with the subject John, the helper verb does, and a whole verb phrase where the verb is like and the object is Mary. The machine has actually understood.
Now, this wasn't just some theory stuck in a lab. The power of the ATN was immediately put to the test on one of the most exciting scientific projects of the entire era.
You see, just 2 years after Woods published his paper, his work became the engine for a system that was frankly revolutionary.
It was called the lunar system, and it was incredible. It let actual geologists sit down and ask plain English questions about the chemical analysis of the moon rocks, the real moon rocks, brought back by the Apollo 11 crew. This was the ultimate proof. The ATN could handle complex, messy, real-world scientific questions.
So you see, the Augmented Transition Network wasn't just a clever program. It was a foundational shift in thinking that would pave the way for the next 50 years of computer science.
I mean, think about it. The ATN was the first model that could handle the crazy recursive nature of our language while building a deep analysis of its meaning, all at the same time. It was so powerful, in fact, that it was proven to be equivalent to a Turing machine, which is basically the theoretical limit of what any computer can do. Every single time your phone understands a command or a search engine figures out your question, it is standing on the shoulders of the work done in that Harvard lab back in 1969.
But for all of its incredible power, the ATN had one major limitation. Every single rule, every condition, every action, it all had to be painstakingly programmed, by hand, by a human. The machine was a genius at executing the grammar, but it couldn't learn it. Which leaves us with the next great question in this journey. What would it take for a machine to finally learn the rules all on its own?